Hello friends, I hope you are enjoying and understanding all the videos. So today we'll see one very important topic in the signals and system, which is convolution integral. Okay, so we always use a system like this, which is called as LTI system, which is linear time invariant system, and we are giving some input to it x of t, and we are getting some output which is dependent on this characteristic of the system. Okay, so x of t is somehow modified by this characteristic that we don't know now what are the characteristic of the system. We want to find out that characteristic of the system by which we are getting a specific output y of t. So it is dependent on this characteristic that whatever input we are given to the system, that is being treated, and we are getting some output which is y of t. So we want to find out that relationship between this input and output. Okay. So simple way to find out the characteristic of the system is to give some input which is very simple and a basic signal, and we'll find out what is the output, and using that you can find out whatever input given to the system, then we'll get a specific output which is y of t. Okay, so suppose a simple input which is equal to del of t. Okay, it is a simple impulse signal which is given as an input to the system, then we'll get, assume it is h of t. Okay, so when we are giving input as some simple signal which is impulse signal, so the response to the impulse is called as impulse response of the system. So impulse response of the system is h of t. Okay, you have referred this h of t many times while studying signals and system. So it is a basic response which is impulse response of the system. Okay, so why impulse signal is chosen? Because we can represent any signal x of t in terms of weighted and shifted impulse signal. Okay, so that we have seen in the last video how to do that. You can refer to that video. So let us assume the first or basic input x of t, it is producing our output y of t. Now we'll give a simple input del of t and we'll get h of t. Okay, so while this derivation, we will assume that it is written here that the system is linear and time invariant. So you know what is linear? A linear system follows the principle of superposition. So what is the principle of superposition? It must follow two properties, that one is scaling or homogeneity and other is additivity. So scaling refers to, if I input to the system instead of x of t, I do a into x of t, then it should produce a into y of t. So it is scaling or homogeneity. Multiplication by a constant produces the same constant multiplying the output of the system. Okay, and what is additivity property? If suppose we are giving input to the system like a1 x1 of t plus a2 x2 of t, then the system in whole produce a1 y1 of t plus a2 y2 of t. Okay, so this system is following homogeneity as well as additivity property. Okay, so this system we can call linear system. Okay, and what is time invariant system? If I am giving some delayed input x of t minus some constant t0, x of t minus t0, then at the output I will get y of t minus t0. So this is time invariance. So we are going to use these two properties. Because the system is LTI, we will apply these properties on this input and we'll check what happens here. So firstly, we'll delay this del of t minus tau. There is a delay of tau here. So what happened at the output? H of t minus tau. this response is also getting delayed by constant tau. Okay. So now this is, I'm using time invariance. Now I'll use scaling property. I will scale this input by some factor. Let us say x of tau. X of tau is the amplitude of at specific instant tau. So I'm multiplying it to this shifted version. So at the output I'll get multiplication by the same constant here, x of tau h of t minus tau. Now I'll use the additivity property. So I'll give a lot of signals like x of t1 del of t minus tau 1, x of tau 2 del of tau t minus tau 2, like this. So as this is continuous time system, I'll use integration starting from minus infinity to infinity. I'll vary the values of tau. So here I'm using additivity property. Additivity property. So x of tau del of t minus tau. Okay, d tau. So there are a lot of shifted versions of del of t minus tau, and depending on the value of tau, these are the different amplitudes. Okay, so all these inputs added together means here integrated. At the output also, all that specific outputs for a specific input, all that outputs will get added. Okay. Now observe here this thing, x of tau del of t minus tau. In the last video we have seen how to represent a signal in terms of weighted and shifted impulses. Okay, so this is the representation of signal x of t, and as we have having x of t to the input of the system, will get y of t at the output. So we can say that this is nothing but y of t. Okay, so y of t can be expressed in terms of x of t and h of t in this form. Okay, so we'll write the formula for y of t. Y of t is equal to integration tau starting from minus infinity to infinity, x of tau h of t minus tau d tau. So this is the relationship where searching for the relationship between the input and output depending on what are the characteristic of the system. So this is the relationship we can write like this: y of t is equal to x of t convolved with h of t. Okay, so this is the formula we will call convolution integral. This is the convolution integral, the relationship between the input, output and the impulse response of the system. So we observe every time here LTI system, the impulse response of the system is given as h of t. We write just behind this LTI system h of t. So h of t is the impulse response of the system. So you can express the output in terms of input and impulse response as a convolution integral. Okay, so in the next lectures we'll see more examples on this convolution integral when the input and impulse response of the system is given, and we also see the properties of convolution integral. So this is the sign of convolution. Okay, so hope you'll be joining me for the more videos. Thank you.